So today we're gonna consider edge colorings. So title is of the today talk is edge colorings. So as we can color vertices, we can color edges as well as. Sorry? Yeah, okay, yeah. In case of troubles, here's. Okay. So, when we color edges, we have one requirement that, let's say we have like vertex, and this is the edges at the vertex U, yes? So what we want all of them to be colored different colors, yes? Blue, green, brown, purple, orange, yes? So all different colors. Okay? So, and we of course want to use the smallest possible number of colors. And then this smallest possible number of colors to use it is called chromatic index, yes? So we define it definition, the smallest possible number of colors to color the edges of G properly. So this is properly when we color all these at every vertex we color the edges to that vertex all differently, yes? That is a proper coloring, yes? Okay, and the smallest possible number of colors to color the edges of G properly, of G, I forget to put here, of G, yes, is called the chromatic index, the chromatic index of G, yes. So we define this term here, yes, and we denote it by this way of this chromatic index, yes. Okay, how call in English this? How you call in English? Prime, or what is prime? Yeah, ski prime. Yeah. Okay. Okay. So one obvious thing is that if we have vertex of degrees 6, yes, one obvious thing is that chromatic index of this graph G will be at least 6, yes? Do we agree? So we have a look in the biggest degree. If it is 10, then we know that chromatic index is at least 10. So let's get a few examples of coloring graph, yes, like C4, C5, just to get Q3 examples, yes. This is a trivial example. K4, and K5. So you can help me to color these graphs, okay? So C4, how many colors we're gonna need? The minimum number of colors. 2, yes. Red, blue. Actually, this holds for every even cycle. So So chromatic index of even cycle is always 2. Okay. What about C5? Can we do it with 2? With 1? No. So we can put one green, and then we go alternatively this way. So we do it with 3. So actually we can do it for every odd cycle with 3, and this is required number. What about this cube? Okay, it is 3, that's true. We can easily color like this. Q3, chromatic index of Q3 is a 3. Probably it can generalize for every hypercube of dimension D, the chromatic index is D. Yes. Okay, let's go to these 2 complete graphs. For the first one, we need how much? We can color like this. We can color like this. We can color like this. Okay? So we use here 3 colors. And what about K5? How many? Can we do it with 4? We cannot do it with 4, yes? But we can do it with 5. I take for each color class and maybe some black one. This is like this. Anybody see why we cannot do it with 4? Do anybody know? Okay, we'll leave it then for the exercises, yes. So what we said before, in general, not only on the example, it holds that chromatics number of G is at least delta, or the maximum degree. This is kind of proposition, yes. Okay, we agree with this. This is trivial. Now, do we know what is line graph? Everybody knows what is line graph? Yes, no? Somebody doesn't know what is line graph? Okay, so line graph, let's repeat it fastly. Line graph. So small subtitle, line graph. Line graph. This is small subgraph. So if we have a graph, G, we do line graph LG by putting on every edge a vertex in the middle, and then connect two blue vertices if the corresponding edges share a common end vertex. Yeah, so it will be like this. Yes, it will be like this. Yeah, so this graph, this diamond graph, is a line graph of our previously drawn graph. Yes. So do you know that and here I've called the following proposition for every graph G, it holds that chromatic index of G is equal chromatic number of LG. And this is obvious, more or less obvious, like when we color vertices of the blue graph, we actually cover the edges of this original graph. And two blue vertices are adjacent if corresponding edges share an end vertex. So coloring the blue adjacent to two blue vertices differently, that is the same like coloring corresponding edges that share one vertex differently, and that's it. So this is in a way, if we have a function to color vertices of the graph, we can also with that function color the edges of the graph. Just make first line graph and then color the vertices of this line graph. Okay? All right. That's one very important graph here in edge colorings because there are very several very difficult conjectures. Is the Petersen graph. Petersen graph. Small subtitle, Petersen graph. Let me draw it. So, is it 3H colorable or not? Is it 3H colorable? No? Yes? So I give you one mind proof. So me, and maybe you know Reza Nasser. Reza Nasser, something like that, yeah. But sometimes this notability right strange. This is, we excellently find this proof that I'm going to prove that it's not rich colorable. It's very original proof. You know it? You don't know it. So it's something like this. Of course, it's not a big deal, but you know, if you have a cubic graph, and it's 3H colorable, okay? And this is some edge, yes. And suppose you have here the color A, colors are A, B, C color, yes. Then you have to have here or here color A appearing, yes. Do we agree? Yes. Now like this. Suppose I like to color with 3 colors this graph. Because this is 5 cycle, all 3 colors will appear somewhere, like A, B, C, yes. Okay? Because this is A, here will be A, and here will be A, by this. A will appear twice inside, in this inside part. This is B, or somewhere else. Because B must appear, and then if it appear here, let's say B appear twice, once here and once here, yes? Also C appear twice inside. So we have 3 colors, A, B, C, each appear twice. So inside we need to have 6 edges. But 5 is smaller than 6, yes? So you cannot color it. So without trying to color it and case analysis, yeah, if this is that, it is like just a counting argument that it is not rich colorable. Do you understand the proof? Is it okay? So it's kind of counting argument. She did it. We even published. Okay. So, but can we color it with 4 colors? Can we color it with 4 colors? You can help me to color it with 4 colors? I'm old and tired and you are fast. Can you help me to color it with 3 colors? You know, sometimes it's like move some unexpected move is doing. So 1, 2, 1. You see? It's going so slow. Okay. So I'm trying on random, yes. I will get stuck it, and then I hope to use the fourth color. Maybe should I use it here? Maybe should I use it here? I don't know. And I put here 3, then I put here 2, I put here 1, I hit. You should be careful that I don't make mistake. I cannot put. Can I put here 3? Okay, 3 to 4. 4. Maybe I can put here 1. I can put here 1 probably, and I can put here probably 2. Is it okay? 1, 2, 4, 3, 1, 2, 1, 2, 3, 2, 1, 3, 2, 3, 4. It looks to me okay. So actually, it is very one important theorem which says it will be always delta plus 1 colorable the graph, and we know that's Vizing theorem, yes. But we go before the Vizing. Look what we had here in these examples. This is of maximum degree 2 and needs 2 colors. This is of maximum degree 3 and needs 3 colors. It's enough 3 colors. Both of these graphs are bipartite. So there is something which says if G is a bipartite graph, then chromatic is delta. Yeah? So this is, call it conic theorem. Conic theorem, yes. Conic theorem. Conic theorem. So, title, yes. So, theorem is of conic, of course. It says for every bipartite graph G, yes, it holds chromatic index of G is equal to the maximum degree. So we may try to prove it now, yes, okay? So proof, okay, suppose we have covered all edges except the last one, yes, but we go by induction the edges. It's obviously true for small graphs with 1 edge, 2 edge, 3 edge, yes, so we don't have to check that. So suppose we color it all edges except some UV, yeah. Suppose we color it all edges of G except UV, yes. Okay. So we use our colors. Our color set is delta, not to delta, yes. Exactly to delta, yes. This is our colors, yes. So I denote by O or U colors. that are missing at vertex U. So they don't appear in this coloring at U. And similarly, this is the colors that don't, in this coloring don't appear at vertex V, yes? So we have situations like this, yes? It's very strange something with this pencil. So we have situations like this is left side of the bipartite graph, this is the right side of the bipartite graph, and we have here the edge E, yes, U and V. Okay? Now, first, if O of U is, and this, okay, these two sets are obviously not empty, yes? Because at vertex U, we have spent it at most delta minus 1 colors, we have delta colors are available, so it has at least one element, and O of V also at least one element, yes? Now, okay, so these two sets, let's say these two sets are non-empty, yes? We can correct this. Are non-empty, yes? Let's say this way, yes? And the second thing is, they have empty intersection. Because if color A is missing here, if A's belong to the intersection, so color A doesn't appear here, color A doesn't appear here, so we put color A here and we are done, yes, okay? This is. Now, second important thing to notice, we denote this notation Hij. In the graph G, we look all edges colored with I and J, and we can observe that these graphs looks like this. Maybe some paths, alternating I, J, and so on maybe. Or there are some, this is first option, these are just a path. Or second option, this path closes. So we get even cycle. I, J, okay? Of any length. It can be length 6, 8, 4, and so on. So whenever we, in the coloring, edge coloring, we choose two colors, we see that these two colors induces some paths and some even cycles. Okay? Okay. So let's say like this. I belongs to, is missing at U, and J is missing at V. This is V. I maybe didn't know. This is vertex V, yes? This is vertex U. And now like this, what we know by this claim, the intersection must be empty. So if I is missing at U, then I must appear at V. So we're gonna have here I, yes? And now there will be maybe some, at this vertex, maybe it has J. At this vertex, we see the induced component of I and J, which contain this edge. Yeah? So it may go like this and maybe stop here. What we do in that case? In that case, we will change this into J, we will change this into I, into J, recolor it into I. Okay, this is J, and here is missing I, so we can put it here, I, and color it. Okay, so this is not just path. Any path finishes somewhere. So this path how to clean it? I cannot use this cleaner. So how we started here? We started with I removed too much. We started with I, J, and this thing, it finished somewhere. It will be great. Yes, we can change it. And then from other side, we have also so. It doesn't stop like that. So from other side, we have also because it's missing here, here must be JS, we will have some part like this. Okay. So here is now J. So I will not have a cycle, okay? These purple things will not be cycled because I don't have J here. Also these brown things, I can apply the same trick to recolor it, cannot finish as a cycle because here is not I, yes, at this vertex, yes, only J. So only possible difficulty is like maybe these two things are glued together into a path. Now this path, look how start. Start, let's say at U. Start at U, and you have J, then I, J, then I, and how it finished, if it finished at V, let's say we proceed a little bit more, and here is V, yes, and finish at V with the color I. How many edges I have here? JI, 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 even edges. This part has even edges, if it is possible. And then I take this additional inside. What I make then? When I put that, I made cycle. This purple brown thing, and when I put this green edge, I get cycle of what length? Odd length, and that's a contradiction because it's bipartite graph. So this is not possible. So eventually we have this part, or this part is just a part in this Hij, and so we can recolor it, and that's it. So this is the Conning theorem. This is the first classical theorem that everybody has to know it. Yes. Okay. What is next theorem? What is this? The next. What is the most important theorem? I call it Vizing. You call it Vizing. Okay, whatever. Subtitle Vizing. I call it Vizing. Okay. Look how unexpectedly it moves. I don't know what I'm doing. Just look. It takes me a lot of time. Yes. So theorem, Vizing, of course. J is simple. Then chromatic index is at most maximum degree plus 1. Okay. We try to do a short proof of it, yes, like kind of sketch of the proof, yes. So we go again by induction. Okay, let's get stuck at the last edge. We color everything, but we get stuck at the last edge. And the last edge looks like this. Let's say this is like VW1, yes. Okay. And of course, colors that are missing at V intersection the colors that are missing in W1. This is HE1. This is empty set. If we have a common color, we put it here, we color it, and we are done. Okay, so we may assume that okay, I don't know what I'm doing. Something, how I can clean now this. I try this way. Maybe I touch something and something is happening with this. So you can still watch. Yes, this is okay. So let's say alpha is missing or is belongs to V. So alpha is missing at V, and let's say B1 is missing in OW1. Okay. And then we have but they are not, alpha doesn't missing here, and beta 1 doesn't missing at VS. So then we're gonna have like some H at V, of course, color it beta 1, and some H in W1 color it alpha, yes. We're gonna consider this H alpha beta 1. And of course, if a component at V goes somewhere and disappears somewhere, gets stuck it, yes, then I can swap again. This is called Kempe chain, yes. Tomorrow we're gonna officially introduce Kempe chain. I'm gonna swap the things here, alpha, beta 1, alpha, beta 1. I'm gonna swap into alpha, beta 1, alpha, beta 1, so on, and put here beta 1, and I'm done. Okay. So I cannot do that. If I cannot do that, what is left? If I cannot do that, what is left? That I have this beta 1, we said alpha, and this is H alpha beta 1, some alternating path, yes. So we have here alpha, beta 1, so on. Okay, so what I do? I will move this color here. Okay, this is called the vertex W2, yes. But then at W2, some color is missing, yes. And now these two, V and W2 will have empty intersection, the missing colors, yes. So let's say BT2 is missing at W2, so it belongs to the OW2, yes. And we know that beta 2 must appear at V. If beta 2 doesn't appear at V, we put here beta 2 and we are done. So beta 2 must appear here. So we have some edge here, W3. This is E2, this is E3, and beta 2 appears here at V. And then we're going to have again Kempe chain here, alpha, and we come to that vertex. To that vertex we come. With this alpha 2. No, alpha beta 2. Yes. Okay. And then we're going to move color beta 2 to E2. Yes. Now this is not colored. E3 is not colored. We're going to do that over and over and over again. But we cannot do that infinitely. So we're going to have here W4, W5, and we'll come to some WK, let's say. And when we do these two, because it's a finite procedure, delta is finite number, it's going to happen one of two things. First thing is, let's say, we at vertex EK, which is like V, WKV, we're going to have, it may happen, and color, and there is missing color beta K, and we're going to have one of two things, like beta K is missing in V, at V, and other scenario is beta K is equal to some previously beta I, yes, where is I smaller than chi minus 1 or something like that. Yeah, okay? So, let's say, in this case, okay, of course, we have here alpha, and then beta K, this chain, alpha and beta K, yes? We see this H alpha beta K. So if beta K is missing at V, here is no beta K, yes? Then I will put here beta K, and I have colored the graph. I did that several times before. So we may assume that, so this case is done, yes, then. In this case, I can do it. Because at VK, at VK is missing beta K, and at V is missing beta K, then I can put here beta K, and I color this edge. Everything else is colored because I was moving this color here, moving this color here, moving here, here, and so on. And I moving the previous color here, beta K minus 1, which was here somehow. I move it somehow like that, yes. So in this case, beta k is bi. Let's for simplicity, not to draw another drawing, assume I is equal to 2. Okay? So look, beta k, so beta t is equal to beta 2 is equal to beta k, yes. So, but you know, we have now here we have this Kemper chain here, alpha beta k, or beta 2, which is the same. We have here beta 2, and then we move with beta 2 here, yes. Now we see this other chain, yes. Beta k, wk doesn't belong here. Because it is not one of these vertices and cannot belong here, because every vertex here is adjacent to some alpha in adjacent to some beta k. Okay? And this is adjacent only to alpha. This is not adjacent to beta k. Okay? And in that case, so I can just put so what I do in that case, I can then, alpha doesn't appear, so swap the cursor in the component alpha beta I, this wk, okay, wk. So I swap here, in that case, I swap here beta k, alpha, beta k, alpha, and then I put here alpha, and that's it. So this is kind of sketch of the proof. If we want properly to do this proof, we should do a little bit, 20 minutes more maybe, yes, but we cannot afford so much time, so you get the idea. So we just do a lot of Kempe chains, swapping the colors around the vertex V, and then we have some free, some chain that cannot appear here, and then we freely move the colors. It is something like this Vizing theorem. Okay, so we have that. So we have that Vizing theorem, which says, and this is very nice. So we have a simple graph. What we know, G simple graph. Then we know that chromatic index is equal to delta or delta plus 1, okay? Delta plus 1. So, and this is this is a question. It's a given graph. G is a given graph. Is it this or is it delta plus 1? So for every graph, we can ask ourselves, is it delta or delta plus 1? And then we define, to be more formal, class 1 graphs if have delta. And then similarly define class 2 graphs if equal delta plus 1. So we can say now Peterson graph belongs to class 2, yes. Hypercube belongs to class, every bipartite graph belongs to class 1, yes. So, okay. And So what is known about these two classes? What is known about these two classes is that to decide, let's say this way, first, what is known, what holds, what holds, holds the following, holds, or maybe holds, change the color. First, almost all graphs are simple graphs, we mean here, are class 1. Okay, that was done by Erdős and Wilson. No, here it's O. Erdős and Wilson. It is NP hard to decide of which classes to characterize. It is NP hard to characterize class 1, let's say. It is NP hard to characterize. So which I so probably that, so that means there is not nice characterization. Oh, the class 1 looks like this and this, yes. You have to check each graph somehow. You can color it maybe with Vizing, but you cannot say, you cannot describe nicely this class of graphs, yes. Okay, so now multigraphs, edge coloring of multigraphs. How almost all graph, this means we can say like this, graphs on n vertices let's say the number of graphs on all vertices, on n vertices, and the same graphs on n vertices that class 1. Okay. Consider the number of class n, yes, given.
Or finite?
Graphs on n vertices that are of class 1 over the whole number of graphs on n vertices, I would say with the labeled graphs, yes. So vertices are labeled 1, 2, 3, n. So usually like this Erdős is doing, Erdős is doing usually. But and then in this counting, this is going, this ratio is going towards 1. So if you could, for every n s to infinity, the graphs which are class 2 over the all graphs on n vertices is 10 to 0. They are very sparse, more and more, yeah. More so if you take the random sum graph on n vertices, as n is increasing, probability that you choose class 1 graph will be almost 1. Something like that, okay? So I don't know the proof, I don't know much details, but usually Paul Erdős is always denote the vertices 1, 2, 3 up to n, and now he take a random graph from here, and then choose with some probability which is 10 towards 1 when n is increasing, that this graph is of class 1.
Construction of say finite number of class 2 graphs.
Do we have a construction of?
It's like how many graphs in class 2? Are they finite or?
They are infinite. Yes, they are infinite. Yeah, but this is not a big deal. Yes.
Next.
This is not a big deal. I mean, there are some construction with critical graphs. You put somewhere vertex on this way or that way. Even we will see for delta for snarks. For snarks, yes, now we have infinite many snarks, yes, it's a cubic graph, yes, and they are all of class 2, yes, and then you can do the same, like, of course, I mean, if you take complete graphs, for n is even, it is class 1, for n is odd, it's class 2. Does that satisfy your question? Okay, so, and there is many other, there are enormously many construction.